Chapter 8 Motion. In everyday life, we see some objects at rest and others in motion. Birds fly, fish swim, blood flow through veins and arteries, and cars move. Atoms, molecules, planets, stars, and galaxies are all in motion. We often perceive an object to be in motion when its position changes with time. However, there are situations where the motion is inferred through indirect evidence. For example, we infer the motion of air by observing the movement of dust and the movement of leaves and branches of trees. What causes the phenomena of sunrise, sunset, and changing of seasons? Is it due to the motion of the earth? If it is true, why don't we directly perceive the motion of the earth? An object may appear to be moving for one person and stationary for some other. For the passenger in a moving bus, the roadside trees appears to be moving backwards. A person standing on the roadside perceives the bus along with the passengers as moving. However, a passenger inside the bus sees his fellow passengers to be at rest. What do these observations indicate? Most motions are complex. Some objects may move in a straight line. Others may take a circular path. Some may rotate and a few others may vibrate. There may be situations involving a combination of these. In this chapter, we shall first learn to describe the motion of objects along a straight line. We shall also learn to express such motions through simple equations and graphs. Later, we shall discuss ways of describing circular motion. Activity 8.1. Discuss whether the walls of your classroom are at rest or in motion. Activity 8.2. Do this. Have you ever experienced that the train in which you are sitting appears to move while it is at rest? Discuss and share your experience. Think and act. We sometimes are endangered by the motion of objects around us, especially if that motion is erratic and uncontrolled as observed in a flooded river, a hurricane, or a tsunami. On the other hand, controlled motion can be a service to human beings, such as in the generation of hydroelectric power. Do you feel the necessity to study the erratic motion of some objects and learn to control them? 8.1 Describing motion. We describe the location of an object by specifying a reference point. Let us understand this by an example. Let us assume that a school in a village in 2 kilometers north of the railway station. We have specified the position of the school with respect to the railway station. In this example, the railway station is the reference point. We could have also chosen other reference point according to our convenience. Therefore, to describe the position of an object, we need to specify a reference point called the origin. 8.1.1 Motion along a straight line. The simplest type of motion is the motion along a straight line. We shall first learn to describe this by an example. Consider the motion of an object moving along a straight path. The object starts its journey from O, which is treated as its reference point. Figure. Let A and B and C represent the position of the object at different instants. At first, the object moves through C and B and reaches A. Then it moves back along the same path and reaches C through B. Figure Positions of an object on a straight line path. O, C, B, A kilometer. The total path length covered by the object is OA plus AC, that is 60 km plus 35 km equal to 95 km. This is the distance covered by the object. To describe distance, we need to specify only the numerical value and not the direction of motion. There are certain quantities which are described by specifying only their numerical values. The numerical value of a physical quantity is its magnitude. From this example, can you find out the distance of the final position C of the object from the initial position O? This difference will give you the numerical value of the displacement of the object from O to C through A. The shortest distance measured from the initial to the final position of an object is known as the displacement. Can the magnitude of the displacement be equal to the distance traveled by an object? Consider the example given in figure. For motion of the object from O to A, the distance covered is 60 km and the magnitude of the displacement is also 60 km. During its motion from O to A and back to B, the distance covered 60 km plus 35 km equal to 85 km. While the magnitude of this displacement equal to 35 km. Thus, the magnitude of displacement 35 km is not equal to the path length 85 km. Further, we will notice that the magnitude of the displacement for a course of motion may be 0, but the corresponding distance covered is not 0. If we consider the object to travel back to O, the final position coincides with the initial position and therefore the displacement is 0. However, the distance covered in this journey is OA plus AO equal to 60 km plus 60 km equal to 120 km. Thus, two different physical quantities, the distance and the displacement, are used to describe the overall motion of an object and to locate its final position with reference to its initial position at a given time. Activity 8.3. Do this. Take a meter scale and a long rope. Walk from one corner of a basketball court to its opposite corner along its sides. Measure the distance covered by you and magnitude of the displacement. What difference would you notice between the two? In this case, activity 8.4. Do this. Automobiles are fitted with a device that shows the distance traveled. Such a device is known as an odometer. A car is driven from Bhubaneswar to New Delhi. The difference between the final reading and the initial reading of the odometer is 1850 km. Find the magnitude of the displacement between Bhubaneswar and New Delhi by using the road map of India. Questions 1, 2, 3. Comment this. Eight point 1.2. Uniform motion and non-uniform motion. Consider an object moving along a straight line. Let it travel 5 meters in the first second, 5 meters more in the next second, 5 meters in the third second, and 5 meters in the fourth second. In this case, the object covers 5 meters in each second. As the object covers equal distances in equal intervals of time, it is said to be in uniform motion. The time interval in this motion should be small. In our day-to-day life, we come across motions where objects cover unequal distances in equal intervals of time. For example, when a car is moving on a crowded street or a person is jogging in a park, these are some instances of non-uniform motion. Activity 8.5. Do this. The data regarding the motion of two different objects A and B are given in table. Examine them carefully and state whether the motion of the objects is uniform or non-uniform. Table: time, distance traveled by object A in m, distance traveled by object B in m. 9:30 am 10:12, 9:40 am 20:19, 10 am 30:33, 10:15 am 40:35, 10:30 am 50:37, 10:45 am 60:41, 11 am 70:44. 8.2 Measuring the rate of motion. A. Speed limit 50 km per hour, 40 km per hour. B. Figure. Look at the situation given in figure. If the bowling speed is 143 km per hour in figure A, what does it mean? What do you understand from the signboard in figure B? Different objects may take different amounts of time to cover a given distance. Some of them move fast and some move slowly. The rate at which objects move can be different. Also, different objects can move at the same rate. One of the ways of measuring the rate of motion of an object is to find out the distance traveled by the object in unit time. This quantity is referred to as speed. The SI unit of speed is meter per second. This is represented by the symbol meter per second or meter per second inverse. The other units of speed include centimeter per second, centimeter second inverse, and kilometer hour inverse. To specify the speed of an object, we require only its magnitude. The speed of an object need not be constant. In most cases, objects will be in non-uniform motion. Therefore, we describe the rate of motion of such objects in terms of their average speed. The average speed of an object is obtained by dividing the total distance traveled by the total time taken, that is, average speed equal to total distance traveled by total time taken. If an object travels a distance s in time t, then its speed v is v equal to s by t. Let us understand this by an example. A car travels a distance of 100 km in 2 hours. Its average speed is 50 km per hour. The car might not have traveled at 50 km per hour all the time. Sometimes it might have traveled faster and sometimes slower than this. Example 8.1. An object travels 16 meters in 4 seconds and then another 16 meters in 2 seconds. What is the average speed of the object? Solution. Total distance traveled by the object 16 meters plus 16 meters equal to 32 meters. Total time taken 4 seconds plus 2 seconds equal to 6 seconds. Average speed equal to total distance traveled by total time taken equal to 32 meters by 6 seconds equal to 5.33 meters per second. Therefore, the average speed of the object is 5.33 meters per second. 8.2.1 Speed with direction. The rate of motion of an object can be more comprehensive if we specify the direction of motion along with its speed. The quantity that specifies both these aspects is called velocity. Velocity is the speed of an object moving in a definite direction. The velocity of an object can be uniform or variable. It can be changed by changing the object's speed, direction of motion, or both. When an object is moving along a straight line at a variable speed, we can express the magnitude of its rate of motion in terms of average velocity. It is calculated in the same way as we calculate average speed. In case the velocity of the object is changing at a uniform rate, then average velocity is given by the arithmetic mean of initial velocity and final velocity for a given period of time, that is, average velocity equal to initial velocity plus final velocity by 2. Mathematically, VAV equal to U plus V by 2, where VAV is the average velocity, U is the initial velocity, and V is the final velocity of the object. Speed and velocity have the same units, that is, meter per second or meter second inverse. Activity 8.6. Do this. Measures the time it takes you to walk from your house to your bus stop or the school. If you consider that your average walking speed is 4 km per hour, estimate the distance of the bus stop or school from your house. Activity 8.7. Do this. At a time when it is cloudy, there may be frequent thunder and lightning. The sound of thunder takes some time to reach you after you see the lightning. Can you answer why this happens? Measure this time interval using a digital wristwatch or a stopwatch. Calculate the distance of the nearest point of lightning. The speed of sound in air equal to 346 meter per second. Questions 1, 2, 3, 4, 5. Comment this. Example 8.2. The odometer of a car reads 2000 km at the start of a trip and 2400 km at the end of the trip. If the trip took 8 hours, calculate the average speed of the car in km per hour and meter per second. Solution. Distance covered by the car is equal to 2400 km minus 2000 km equal to 400 km. Time elapsed t equal to 8 hours. Average speed of the car is VAV equal to S by T 400 km by 8 hour equal to 50 km per hour. Equal to 50 km per hour into 1000 meter per 1 km into 1 hour by 3600 second equal to 13.9 meter per second. The average speed of the car is 50 km per hour or 13.9 meter per second. Example 8.3. Usha swims in a 90-meter long pool. She covers 180 meters in 1 minute by swimming from one end to the other and back along the same straight path. Find the average speed and average velocity of Usha. Solution. Total distance covered by Usha in 1 minute is 180 meter. Displacement of Usha in 1 minute equal to 0 meter. Average speed equal to total distance covered total time taken equal to 180 meter per 1 minute equal to 180 meter per 1 minute into 1 minute per 60 second equal to 3 meter per second. Average velocity equal to displacement by total time taken equal to 0 meter by 60 second equal to 0 meter per second inverse. The average speed of Usha is 3 meter per second and her average velocity is 0 meter per second. 8.3. Rate of change of velocity. During uniform motion of an object along a straight line, the velocity remains constant with time. In this case, the change in velocity of the object for any time interval is 0. However, in non-uniform motion, velocity varies with time. It has different values at different instants and at different points of the path. Thus, the change in velocity of the object during any time interval is not 0. Can we now express the change in velocity of an object? To answer such a question, we have to introduce another physical quantity called acceleration, which is a measure of the change in the velocity of an object per unit time. That is, acceleration equal to change in velocity by time taken. If the velocity of an object changes from an initial value u to the final value v in time t, the acceleration a is a equal to v minus u by t. This kind of motion is known as accelerated motion. The accelerated is taken to be positive if it is in the direction of velocity and negative when it is opposite to the direction of velocity. The SI unit of acceleration is meter per second square. If an object travels in a straight line and its velocity increases or decreases by equal amounts in equal intervals of time, then the acceleration of the object is said to be uniform. The motion of a freely falling body is an example of uniformly accelerated motion. On the other hand, an object can travel with non-uniform acceleration if its velocity changes at a non-uniform rate. For example, if a car traveling along a straight road increases its speed by unequal amounts in equal intervals of time, then the car is said to be moving with non-uniform acceleration. Activity 8.8. Do this. In your everyday life, you come across a range of motions in which A. Acceleration is in the direction of motion. B. Acceleration is against the direction of motion. C. Accelerated is uniform. D. Acceleration is non-uniform. Can you identify one example each for the above type of motion? Example 8.4. Starting from a stationary position, Rahul pedals his bicycle to attain a velocity of 6 meters per second in 30 seconds. Then he applies brakes such that the velocity of the bicycle comes down to 4 meters per second in the next 5 years. Calculate the acceleration of the bicycle in both the cases. Solution. In the first case, initial velocity u equal to 0, final velocity v equal to 6 meters per second, time t equal to 30 seconds. From equation, we have a equal to v minus u by t. Substituting the given values of u, v and t in the above equation, we get a equal to 6 meters per second minus 0 meters per second by 30 seconds equal to 0.2 meters per second square. In the second case, initial velocity u equal to 6 meters per second, final velocity v equal to 4 meters per second, time t equal to 5 seconds. Then a equal to 4 meters per second minus 6 meters per second by 5s equal to minus 0.4 meters per second square. The acceleration of the bicycle in the first case is 0.2 meters per second square, and in the second case it is minus 0.4 meters per second square. Questions 1, 2, 3. Comment this. 8.4. Graphical representations of motion. Graphs provide a convenient method to present basic information about a variety of events. For example, in the telecast of a one-day cricket match, vertical bar graphs show the run rate of a team in each over. As you have studied in mathematics, a straight line graph helps in solving linear equations having two variables to describe the motion of an object. We can use line graphs. In this case, line graphs shows dependence of one physical quantity, such as distance or velocity, on another quantity such as time. 8.4.1 Distance time graphs. The change in the position of an object with time can be represented on the distance time graph adopting a convenient scale of choice. In this graph, time is taken along the x-axis and distance is taken along the y-axis. Distance time graphs can be employed under various conditions where objects move with uniform speed, non-uniform speed, remain at rest, etc. Distance kilometer, time minute. Figure distance time graph of an object moving with uniform speed. We know that when an object travels equal distances in equal intervals of time, it moves with uniform speed. This shows that the distance traveled by the object is directly proportional to time taken. Thus, for uniform speed, a graph of distance traveled against time is a straight line. As shown in figure, the portion OB of the graph shows that the distance is increasing at a uniform rate. Note that you can also use the term uniform velocity in place of uniform speed if you take the magnitude of displacement equal to the distance traveled by the object along the y-axis. We can use the distance-time graph to determine the speed of an object. To do so, consider a small part AB of the distance-time graph shown in figure. Draw a line parallel to the x-axis from point A and another line parallel to the y-axis from point B. These two lines meet each other at point C to form a triangle ABC. Now on the graph, FC denotes the time interval T2 minus T1 while BC corresponds to the distance S2 minus S1. We can see from the graph that as the object moves from the point A to B, it covers the distance S2 minus S1. In time T2 minus T1, the speed v of the object therefore can be represented as v equal to S2 minus S1 by T2 minus T1. We can also plot the distance-time graph for accelerated motion. Table shows the distance traveled by a car in a time interval of 2 seconds. Table distance traveled by a car at regular time intervals. Time in second, distance in meters. 0, 0, 2, 1, 4, 4, 6, 9, 8, 16, 10, 25, 12, 36. Distance meter times second. Figure distance time graph for a car moving with non-uniform speed. The distance time graph for the motion of the car is shown in figure. Note that the shape of this graph is different from the earlier distance time graph figure. For uniform motion, the nature of this graph shows non-linear variation of the distance traveled by the car with time. Thus, the graph shown in figure represents motion with non-uniform speed. 8.4.2 Velocity time graphs. The variation in velocity with time for an object moving in a straight line can be represented by a velocity time graph. In this graph, the time is represented along the x-axis, velocity kilometer per hour, time h, figure velocity time graph for uniform motion of a car. And the velocity is represented along the y-axis. If the object moves at uniform velocity, the height of its velocity time graph will not change with time. Figure. It will be a straight line parallel to the x-axis. Figure shows the velocity time graph for a car moving with uniform velocity of 40 km per hour. We know that the product of velocity and time give displacement of an object moving with uniform velocity. The area enclosed by velocity time graph and the time axis will be equal to the magnitude of the displacement. To know the distance moved by the car between time t1 and t2 using figure, draw perpendiculars from the points corresponding to the time t1 and t2 on the graph. The velocity of 40 km per hour is represented by the height AC or BD, and the time t2 minus t1 is represented by the length AB. So the distance S moved by the car in time t2 minus t1 can be expressed as S equal to AC into CD equal to 40 km per hour into t2 minus t1 h. 40 t2 minus t1 kilometer, area of the rectangle ABDC shaded in figure. We can also study about uniformly accelerated motion by plotting its velocity time graph. Consider a car being driven along a straight road for testing its engine. Suppose a person sitting next to the driver records its velocity after every 5 seconds by noting the reading of the speedometer of the car. The velocity of the car in km per hour as well as in meter per second at different instants of time is shown in table. Table velocity of a car at regular instants of time. Time S, velocity of the car meter per second, kilometer per hour. 0, 0, 0, 5, 2.59, 10, 5.0, 18. 15, 7.5, 37, 20, 10.0, 36, 25, 12.5, 45, 30, 15.0, 54. In this case, the velocity time graph for the motion of the car is shown in figure. The nature of the graph shows the velocity changes by equal amounts in equal intervals of time. Thus, for all uniformly accelerated motion, the velocity time graph is a straight line. Velocity kilometer per hour, time second. Figure velocity time graph for a car moving with uniform acceleration. You can also determine the distance moved by the car from its velocity time graph. The area under the velocity time graph gives the distance magnitude of displacement moved by the car in a given interval of time. If the car would have been moving with uniform velocity, the distance traveled by it would be represented by the area ABCD under the graph figure. Since the magnitude of the velocity of the car is changing due to acceleration, the distance S traveled by the car will be given by the area ABCDE under the velocity time graph figure. That is, S equal to area ABCDE equal to area of rectangle ABCD plus area of the triangle ADE equal to AB into BC plus half AD into DE. In the case of non-uniformly accelerated motion, velocity time graphs can have any shape. Velocity meter per second times second A. Velocity meter per second times second B. Figure velocity time graph of an object in non-uniformly accelerated motion. Figure A shows a velocity time graph that represents the motion of an object whose velocity is decreasing with time, while figure B shows the velocity time graph representing the non-uniform variation of velocity of the object with time. Try to interpret these graphs. Activity 8.9. Do this. The times of arrival and departure of a train at three stations A, B and C and the distance of stations B and C from stations A are given in table. Table distances of station B and C from A and times of arrival and departure of the train. Station distance from A kilometer, time of arrival hours, time of departure hours. A 0, 8, 8:15, B 120, 11:15, 11:30, C 180, 13, 13:15. Plot and interpret the distance time graph for the train, assuming that its motion between any two stations is uniform. Activity 8.10. Do this. Firoz and his sister Sania go to school on their bicycle. Both of them start at the same time from their home but take different times to reach the school. Although they follow the same route, table shows the distance traveled by them in different times. Table distance covered by Firoz and Sania at different times on their bicycle. Time distance traveled by Firoz kilometer, distance traveled by Sania kilometer. 8 am 0, 0. At 5 am 1, 0.8. 8:10 am 1.9, 1.6. 8:15 am 2.8, 2.3. 8:20 am 3.6, 3. 8:25 am 3.6. Plot the distance time graph for their motion on the same scale and interpret. Questions 1, 2, 3, 4. Comment this. (8.5) Equations of motion by graphical method. When an object moves along a straight line with uniform acceleration, it is possible to relate its velocity, acceleration during motion, and the distance covered by it in a certain time interval by a set of equations known as the equations of motion. For convenience, a set of three such equations are given below. B equal to U plus AT, S equal to UT plus half AT square, 2AS equal to V square minus U square, where u is the initial velocity of the object which moves with uniform acceleration a for time t, b is the final velocity, and s is the distance traveled by the object in time t. Equation describes the velocity time relation, and equation represent the position time relation equation, which represent the relation between the position and the velocity, can be obtained from equations, and by eliminating t, these three equations can be derived by graphical method. 8.5.1 Equation for velocity time relation. Consider the velocity time graph of an object that moves under uniform acceleration as a d b e velocity meter per second time s. Figure velocity time graph to obtain the equation of motion. Shown in figure similar to figure but now with u not equal to 0. From this graph you can see that initial velocity of the object is u at point A, and then it increases to v at point B in time t, but the velocity changes at a uniform rate a. In figure, the perpendicular lines BC and BE are drawn from point B on the time and the velocity axis respectively, so that the initial velocity is represented by OA, the final velocity is represented by BC, and the time interval T is represented by OC, BD equal to BC minus CD. Represent the change in velocity in time interval T. Let us draw AD parallel to OC. From the graph, we observe that BC equal to BD plus DC equal to BD plus OA. Substituting BC equal to V and OA equal to U, we get V equal to BD plus U or BD equal to V minus U. From the velocity time graph figure, the acceleration of the object is given by A equal to change in velocity by time taken equal to BD by AD equal to BD by OC. Substituting OC equal to T, we get A equal to BD by T or BD equal to AT. Using equations, and we get V equal to U plus AT. 8.5.2 Equations for position time relation. Let us consider that the object has traveled a distance s in time t under uniform acceleration a. In figure, the distance traveled by the object is obtained by the area enclosed within OABC under the velocity time graph AB. Thus, the distance s traveled by the object is given by s equal to area OABC, which is a trapezium, equal to area of the rectangle OADC plus area of the triangle ABD. OA into OC plus half AD into BD. Substituting OA equal to U, OC equal to AD equal to T and BD equal to AT. We get S equal to U into T plus half T into AT, or S equal to UT plus half AT square. 8.5.3 Equation for position velocity relation. From the velocity time graph shown in figure, the distance is traveled by the object in time t. Moving under uniform acceleration a is given by the area enclosed within the trapezium OABC under the graph, that is S equal to area of the trapezium OABC equal to OA plus BC into OC by half. Substituting OA equal to U, BC equal to B and OC equal to T, we get S equal to U plus B of T by 2. From the velocity time relation equation, we get T equal to B minus U by A. Using equations, and we have S equal to B plus U into B minus U by 2A, or 2AS equal to B square minus U square. Example 8.5. A train starting from rest attains a velocity of 72 km per hour in 5 minutes. Assuming that the acceleration is uniform, find 1. The acceleration and 2. The distance traveled by the train for attaining this velocity. Solution. We have been given u equal to 0, v equal to 72 km per hour equal to 20 meter per second, and t equal to 5 minutes equal to 300 seconds. 1. From equation, we know that A equal to V minus U by T equal to 20 meter per second minus 0 meter per second by 300 second equal to 1 by 15 meter per second square. 2. From equation we have 2as equal to v square minus u square equal to v square minus 0. Thus, s equal to v square by 2a equal to 20 meter per second whole square 2 into 1 by 15 meter per second square equal to 3000 meter equal to 3 kilometer. The acceleration of the train is 1 by 15 meter per second square and the distance traveled in 3 kilometer. Example 8.6. A car accelerates uniformly from 18 km per hour to 36 km per hour in 5 seconds. Calculate 1. The acceleration and 2. The distance covered by the car in that time. Solution. We are given that u equal to 18 km per hour equal to 5 meter per second, b equal to 36 km per hour equal to 10 meter per second and t equal to 5 second. 1. From equation we have a equal to b minus u by t equal to 10 meter per second minus 5 meter per second by 5 second equal to 1 meter per second square. 2. From equation we have s equal to ut plus half ft square half at square equal to 5 meter per second into 5 second plus half into 1 meter per second square into 5 second whole square equal to 25 meter plus 120 12.5 meter equal to 37.5 meter. The acceleration of the car is 1 meter per second square and the distance covered is 37.5 meter. Example 8.7. The brakes applied to a car produced an acceleration of 6 meter per second square in the opposite direction to the motion. If the car takes 2 seconds to stop after the application of brakes, calculate the distance it travels during this time. Solution. We have been given a equal to minus 6 meter per second square, t equal to 2 seconds and v equal to 0 meter per second. From equation we know that b equal to u plus at, 0 equal to u plus minus 6 m s inverse 2 into 2 seconds or u equal to 12 meter per second. From equation we get s equal to ut plus half at square equal to 12 meter s inverse into 2 second plus half minus 6 meter per second square 2 second whole square. 24 meter minus 12 meter equal to 12 meter. Thus the car will move 12 meter before it stops after the applications of brakes. Can you now appreciate why drivers are cautioned to maintain some distance between vehicles while traveling on the road? Questions. 1. A bus starting from rest moves with a uniform acceleration of 0.1 meter per second square for 2 minutes. Find A. The speed acquired. B. The distance traveled. Comment this. 2, 3, 4, 5. Comment this. 8.6. Uniform circular motion. When the velocity of an object changes, we say that the object is accelerating. The change in the velocity could be due to change in its magnitude or the direction of the motion or both. Can you think of an example when an object does not change its magnitude or velocity but only its direction of motion? A. Rectangular track. B. Hexagonal track. C. Octagonal shaped track. D. A circular track. Figure. The motion of an athlete along closed tracks of different shapes. Let us consider an example of the motion of a body along a closed path. Figure A shows the path of an athlete along a rectangular track ABCD. Let us assume that the athlete runs at a uniform speed on the straight parts AB, BC, CD and DA of the track. In order to keep himself on track, he quickly changes his speed at the corner. How many times will the athlete have to change his direction of motion while he completes one round? It is clear that to move in a rectangular track once, he has to change his direction of motion 4 times. Now suppose instead of a rectangular track, the athlete is running along a hexagonal shaped path A, B, C, D, E, F as shown in figure B. In this situation, the athlete will have to change his direction 6 times while he completes one round. What if the track was not a hexagon but a regular octagon with 8 equal sides as shown by A, B, C, D, E, F, G, H is figure C? It is observed that as the number of sides of the track increases, the athlete has to take turns more and more often. What would happen to the shape of the track as we go on increasing the number of sides indefinitely? If you do this, you will notice that the shape of the track approaches the shape of a circle and the length of each of the sides will decrease to a point. If the athlete moves with a velocity of constant magnitude along the circular path, the only change in his velocity is due to the change in the direction motion. The motion of the athlete moving along a circular path is therefore an example of an accelerated motion. We know that the circumference of a circle of radius r is given by 2 pi r. If the athlete takes t seconds to go once around the circular path of radius r, the speed v is given by v equal to 2 pi r by t. When an object moves in a circular path with uniform speed, its motion is called uniform circular motion. Activity 8.1, 8.11. Do this. Take a piece of thread and tie a small piece of stone at one of its ends. Move the stone to describe a circular path with constant speed by holding the thread at the other end as shown in figure. A stone describing a circular path with a velocity of constant magnitude. Now let the stone go by releasing the thread. Can you tell the direction in which the stone moves after it released? By repeating the activity for a few times and releasing the stone at different position of the circular path, check whether the direction in which the stone moves remain the same or not. If you carefully note one being released, the stone moves along a straight line tangential to the circular path. This is because once the stone is released, it continues to move along the direction it has been moving at that instant. This shows that the direction of motion changed at every point when the stone was moving along the circular path. When an athlete throws a hammer or a discus in a sports meet, he or she holds the hammer or the discus in his or her hand and gives it a circular motion by rotating his or her own body. Once released in the desired direction, the hammer or discus moves in the direction in which it was moving at the time it was released, just like the piece of stone in the activity described above. There are many more familiar examples of objects moving under uniform circular motion, such as the motion of the moon and the earth, a satellite in a circular orbit around the earth, a cyclist on a circular track at constant speed, and so on. What you have learned? Motion is a change of position. It can be described in terms of the distance moved or the displacement. The motion of an object could be uniform or non-uniform depending on whether its velocity is constant or changing. The speed of an object is the distance covered per unit time, and velocity is the displacement per unit time. The acceleration of an object is the change in velocity per unit time. Uniform and non-uniform motions of objects can be shown through graphs. The motion of an object moving at uniform acceleration can be described with the help of the following equations, namely v equal to u plus at, s equal to ut plus half at square, 2as equal to v square minus u square, where u is initial velocity of the object which moves with uniform acceleration a for time t, v is its final velocity, and s is the distance it traveled in time t. If an object moves in a circular path with uniform speed, its motion is called uniform circular motion. Exercises: do this and comment this. Figure: distance kilometer, time hour. Figure: speed meter per second, time second. Comment this.